This video is analyzing the graph of a function. So when you're sketching the graph of a function, either by hand or with some graphing utility, you have to remember that you can't show the entire graph. So the decision as to which part of the graph you choose to show is really crucial. Let's look at an example here. Say we're looking at the graph of f of x equals x cubed minus 25x squared plus 74x minus 20. Look at these two windows. Both of these are over specific intervals. The first one is from x equals -2 to y equals 5. Okay. The second one, though, is from -10 to 30. And notice that our y value went from over here, we're -10 to 40. Over here, we're -1200 to 200. So it's a much bigger window. Okay. By seeing both of these views, it's clear that the second viewing window gives a better, more complete representation of the graph. Now, here's a question. Would a third different window reveal even more interesting things going on in that graph? Well, to answer this, what you need to do is use calculus to interpret the first and second derivatives. This is going to give us all the information we need to know whether there are turns, bumps, bruises, things like that inside of our graphs. Now, in 112, pretty much all we could do is find the intercepts, find the asymptotes, and just kind of go from there. Pick some points and just kind of figure it out. Now we can actually find points of inflection, so we can talk about concavity. We can find all of the relative maxes and mins. So there's a lot more we can do now. So to determine that good window of the function, we're going to use these guidelines to analyze the graph. First thing, we're going to determine the domain and range of the function, specifically the domain. I'm not so much worried about the range. That's a little bit more challenging to figure out, but the domain is kind of key. We're going to find the intercepts, we're going to find the asymptotes, and we're going to see if there's any kind of symmetry. 9 times out of 10, there's not, but you never know. The next thing we're going to do is we're going to locate our critical numbers and find our relative max and mins. We're going to find our points of inflection. Okay, so using the first and second derivatives, we're going to find mins, max, and points of inflection. So let's do one, jump right in, and see what we can do. So the first thing we're going to do is we're going to look at this. 2x squared minus 2 times x squared minus 9 over x squared minus 4. So right away, interestingly enough, I said it generally doesn't happen, but here, this is an even function. How do we know? Well, for rational functions, we explore top and bottom. So since the top only has even exponents, right? The bottom only has even exponents, because remember, a constant is an even term. It's irrelevant that 9 is an odd number. That's not what I'm talking about. I'm talking about is an even term. So we have an even term or an even function on the top divided by an even function on the bottom. So even divided by even equals even. Odd divided by odd is also even. However, even divided by odd or odd divided by even, both of these are odd. And if there's a neither anywhere, the whole thing is neither. So this one is actually even, which means it has symmetry, right? It has y-axis symmetry. So we know right away it's going to have y-axis symmetry. If you don't recognize that, it's fine. You'll notice it when you get done, okay? So let's start first by finding our intercepts. So we need to find the x-intercepts by setting the numerator equal to 0, right? Why? Because that's just setting y equal to 0. If we're looking for the x-intercepts, that's where y equals 0. So 0 equals this. That only happens when the numerator equals 0. So that gives us 2 times x squared minus 9 equals 0. Divide by 2, factor that, you get x equals plus or minus 3. Now the y-intercepts you find by setting x equal to 0. So this gives us 2 times 0 minus 9 over 0 minus 4, which is negative 18 over negative 4, which is 9/2. Or I don't even have to use approximately. It's exactly 4.5, right? All right, so that finds us our intercepts. Let's jump over and see if we can't find our asymptotes. So our vertical asymptotes are where our denominator equals 0. X squared minus 4 equals 0. I get x equals plus or minus 2. Our horizontal asymptotes, we need to make sure that this is in standard form, 2x squared minus 18 over x squared minus 4. We're going to compare the powers, right? They have the same power, therefore y equals the ratio of the leading coefficients, 2 over 1. So there's our horizontal asymptote. Since this is rational, that's going to be the same on both sides. All right, so right away, we know we have some points we can draw. So we've got x equals plus or minus 3. So 1, 2, 3, 1, 2, 3. Those are our x-intercepts. Our y-intercept is at 4.5. 1, 2, 3, 4, 5. So between 4 and 5. We've got that we have vertical asymptotes at plus or minus 2. Okay. And we have horizontal asymptote at y equals 2. Now, in Math 112, we could have went ahead and graphed it at this point. I can see what the graph is going to look like. If you're not there yet, that's fine. We're going to go ahead and use all of our other information to find maxes, mins, and concavity. So let's do it here. So we need to start by finding the first derivative. So our function is 2x squared minus 18. So let's rewrite the function. 2x squared minus 18 over x squared minus 4, right? So then I need to find f prime. So that's low d high minus high d low over low low. So this gives us 4x cubed minus 16x minus 4x to the fourth plus 36, that should be x cubed, sorry, plus 36x. Let's make sure that's right. 4x times x squared is 4x cubed. 4x times negative 4 is negative 16x. Negative 2x times 2x squared is 4x cubed. Negative times negative is positive 18 times 2x is 36x. All right, over x squared minus 4 squared. The 4x cubes will cancel out. 36 minus 16 gives us 20x over x squared minus 4 squared. So first derivative test, I'm going to set that equal to 0, which means I can ignore the denominator. I know that the numerator 20x has to equal 0. I get that x equals 0. It's my only critical value, the only place where I can have a max or a min. So how do I find it? I go over here. I've got 0, right? No. We're going to have to use the second derivative anyway. Let's wait. Let's don't do the first derivative unless we have to. So let's go ahead and find the second derivative. So low d high minus high d low. We got to multiply the 2 times x squared minus 4, decrease by 1, and then the derivative of inside. All over x squared minus 4 squared low low. So squared. So this is going to give us, let me get this out of the way so I have more room here. This is going to give us 20 times. If we FOIL that out, we get x to the fourth minus 8x squared plus 16. Over here, we're going to have 20 times 2 times 2. So 4 times 20 is negative 80x times x squared minus 4. 20 times 2 is 40, times 2 is 80, x times x is x squared, okay? Over x squared minus 4, squared squared is just to the fourth. So this is going to give us 20x to the fourth minus 160x squared plus 320 minus 80x to the fourth plus 320x squared all over x squared minus 4 to the fourth. Now, we combine our like terms. 20x to the fourth minus 80x to the fourth is negative 60x to the fourth. So that gets rid of the x to the fourths. 160x squared, negative 160 plus 320 is plus 160x squared. So those go away. Plus 320 all over x squared minus 4 to the fourth. Now, we're talking about the second derivative, so we're going to set that equal to 0. So negative 60x to the fourth plus 160x squared plus 320 over x squared minus 4 to the fourth. Now, let's go ahead and do the second derivative test. We're going to plug in our critical number from the first derivative, 0, and see what happens if I plug in f double prime of 0. So that gives me 0 plus 320 over 0 minus 4, but negative 4 to the fourth power is, well, whatever it is, it's positive, right? A positive divided by a positive is positive. Therefore, since I got a 0, that tells me that I'm concave up because it's positive, which means that 0 represents a minimum. And since it's approaching an asymptote, we know it's going to look like that. Now, we're going to set this equal to 0. We're going to say negative 60x to the fourth plus 160x squared plus 320 equals 0 to find our possible points of inflection. Now, if I divide by, let's see, what we'll go into all of those. I know they're all divisible by 2. Are they all divisible by 6? No. 160 divided by... They're all divided by 20? Yeah, they're all divisible by 20. So if I divide negative 20 out, so 60 divided by 20 is going to give me 3x to the fourth. 160 divided by negative 20 is going to give me negative 8x squared. And then 320 divided by 20 is going to give me minus 16 equals 0. Now, the negative 20 can never be 0, so really we're just looking at this. So you've got 3 times negative 16. It's negative 48. So do I have two numbers that multiply to be negative 48 but add to be negative 8? Because this is just quadratic, right? This is a fourth and a square, so this is going to be quadratic in x squared. So negative 48 can be, what? 1 and 48, 2 and 24, 3 and 16. Yeah. 4 and 12. 4 and 12 will subtract to be -8 if the 12 is negative. So we've got, I'm going to use amazing method here. We've got 4 and -12. We put the 3 and the x squared, the 3 and the x squared, and then we simplify. 3 will go into 12 4 times, so we wind up with 3x squared plus 4, and we wind up with x squared minus 4 equals 0, and then -20. Now here, -20 can never be 0, so we can throw it out. 3x squared plus 4 gives me 3x squared plus 4 equals 0. I get 3x squared equals -4. X squared equals -4/3. If I take the square root, I'm going to wind up with an imaginary number, so I can throw that out. I get x squared minus 4 equals 0. I get x equals plus or minus 2. So there are my possible points of inflection. So we're talking about from -infinity to infinity. I care about -2 and +2. So my test points, let's do -3, 0, and +3. And we're going to plug it in to the second derivative. Okay? The whole second derivative. So if I plug in -3, I get, let's see, -3 to the 4th is 81 times -60 plus 160 times -3 squared plus 320 gives me -3100, and then divided by -3 squared is 9, 9 minus 4 is 5, 5 to the 4th power. Let's see, is that right? 9 minus 4 is 5, 5 to the 4th. So we've got I don't feel like this is right. Let me make sure. Let me plug these values back into my calculator. -60 times -3 to the 4th plus 160 times -3 squared plus 320. Yeah, -3100. Oh, remember, I'm trying to make it be a real number. It doesn't have to be a real number. The whole point is just, is it positive or negative? So when you divide that by 5 to the 4th, which is a positive number, you get a negative divided by a positive, which is negative, which means we are decreasing, right? So we started high and we're going low, which means we're concave down, right? If we plug in 0, we get 0 plus 0 is 320 over a positive number. Positive is positive, therefore we are concave up. Therefore, -2 represents a point of inflection from decreasing to increasing. Now, 2 gives us the same exact thing, right? Because all of these values are even. So if we plug in 2, we're still going to get, and I don't want to plug in 2, I want to plug in 3. We're going to get the exact same value that we did for 3, which is still a negative number, which means we're talking about concave up, concave down. Now, I want to show you something. Back to the original function. What is this? X squared minus 4. That means that x equals plus or minus 2 are not defined, right? Which means if I had tried to get plus or minus 2 as the first derivative, they would not have been critical numbers, right? Critical numbers are only the values where the derivative equals 0 or where the derivative doesn't exist, x squared minus 4 squared, it doesn't exist, right, at plus or minus 2, but it also doesn't exist here. So I didn't have to use these values because plus and minus 2 were not in the domain of the original function. If you're asking yourself, why didn't I use them here? That's why, because they're not defined in f. However, remember that for the second derivative, we have to include any value that is not in the domain. So if it's not in the domain here, which it was, I got this exclusion, but even if I had not got this plus or minus, I still would have had to have used plus or minus 2 because those represent asymptotes where things can change. They're not technically points of inflection because those are points where there's an asymptote. So what's really important is to recognize the actual concavity. We're not really going to have points of inflection because points of inflection only occur at those values where the derivative equals 0 or doesn't exist, but do exist in the original function. Since it doesn't exist in the original function, also doesn't exist as a point of inflection. So that gives us a bunch of stuff. Let's go ahead and graph everything we know. So we know there is a asymptotes at x equals -2, +2. We know there is a horizontal asymptote at y equals 2, right? We got 2, 2, and 2. We know we have y-intercepts. Let's do them in different color. Y-intercepts at -3 and +3, or x-intercepts, y-intercept at 4.5. We know that 4.5 represents a minimum, right? We also know that from -infinity to -2, we have concave down. So that means that this has to be concave down, right? Upside down bowl. We also know that on the other side, from 2 to +infinity is concave down. Now, because we have no points of inflection, we know, and this was a problem in 112, we know that it can't go up and then come back down because that would give us a relative minimum. It would also give us a point of inflection. A relative maximum, sorry. Since we don't have those things, we can infer that it doesn't cross over the asymptote and it just hugs it. So if you have any questions about any of this using the first and second derivatives to curve sketch, please shoot me a remind or ask a question in class.